So we'll just wait for a couple of minutes and then I think we can start. So I think we should start. So good afternoon everyone. Yeah, I'll just share. I've not shared it yet. So good afternoon everyone. My name is Musab Rafiq. So today we are going to discuss problems related to week 6 live tutorial. So we are going to discuss problems related to week 6 material. So this is a live session 6. So let me just share the screen first and then I can give a proper intro. So once again I welcome you all to this live session 6. This live session 6 of the course Digital Circuits that is taught by Professor Gautam Saha from IIT Kharagpur, and I am your teaching assistant for this course. My name is Musab Rafiq. I am a PhD student at Department of Electrical Engineering at IIT Kanpur. So we are going to discuss live problems, and I want to make a couple of instructions clear. I think you all know that, but still I have to repeat it. I'll be admitting new participant only after a particular problem is solved, and after every problem I'll give ample time to ask any doubts. Since the number of participants are less, you can ask your doubts using mic, but you can also ask your doubts using the chat box feature. So let me just first go to the Google Meet, and okay, I think we are ready to go. So yeah, so today, as already pre-advertised, we will discuss problems related to week 6. So week 6 will have these things: magnitude comparators, ALU, error detecting and correcting codes. We just wait a second, sorry about this. We'll have problems related to magnitude comparator, ALU, error detecting and correcting codes, and also problems related to some XS3 gray codes and etc. So let's begin with the first problem. So the first problem asks us, in the figure given below, the outputs can be given as. So we have this 4-bit 2's complement subtractor here, and then we have the two output showing this this sum or subtract option from S3 to S0, S3, S2, S1, S0, the 4 bits, and the carry out. And then we have the combinational logic, and based on that combinatorial logic we have these three conditions: x greater than y, x equal to y, and x less than y. So this will be equal to 1 when x is greater than y, this will be equal to 1 when x is equal to y, and this will be equal to 1 when x is less than y. So we know that x, if x is equal to y, and C out is equal to 1, and also this condition is true for x greater than y also. If x is greater, x equal to y, C out is equal to 1. If x is greater than y, C out is equal to 1. So also for x greater than y, if any of the s bit, so from S2, S3 to S0, if any of the bit is 1, that number will be then x is greater than y. So for x greater than y, we have conditions. C out should be equal to 1, that's a necessary condition, and any of the SI should be equal to 1, any of the SI, any. So here I should write any SI. So this can be written as, this whole thing can be written as in the form of a combinational logic like this. So for x greater than y, so C out equal to 1 is a necessity condition, C out equal to 1, so we write C out, and it should be true with this thing, any of this. So when any of the number is any of the bit is 1, the output should be 1, and based on the truth table of OR gate, we can use the OR gate of 4 inputs. So we can have S0 plus S1 plus S2 plus S3. So if you carefully look at this thing means if any of the input, any of the S is 1, this will be 1, and this means when C out is 1, this whole thing will be 1. So this is C out and with OR of this thing. So this is the combination logic for x greater than y. Now for x equal to y, we have a condition, C out is equal to 1 and Si should be equal to 0. All the bits from S3 to S0 should be 0. So this can be written as in the form of a combination logic, S equal to y, so C out equal to 1 just like here, and this thing will be ANDed with S3 complement, S2 complement, S1 complement and S0 complement. So if you carefully look at this logic, this combination logic, this is 1 only when C out is 1 and S3, S2, S1, S0 are all equal to 0, then only is 1. So we have this for x greater than y and this x equal to y. And for x less than y, C out should be equal to 0. There is only one condition. So C out equal to 0 means C out complement. So when C out is equal to 0, this thing will be equal to 1. C out complement. So x less than y is equal to C out complement. So the three conditions are, for x less than y we have C out complement. So these three are the, among these three one of them will be correct. And for x equal to y we have C out, S3 complement, S2 complement, S1 complement, S0 complement, and that is this thing B, and also option C is having that. Now we have to check the third condition, x greater than y, that is C out and with S0 plus S1 plus S2 plus S3, that is this thing. So option B is the correct answer to this question. So any doubts here? Okay, if you have any doubts, please type in. Now we can move forward to question number 2. Yeah. So the question number 2 asks us, the code used to reduce error due to ambiguity in reading of binary optical encoder is A. Octal codes, B. accessory codes, 3. gray code, and 4. BCD code. So the code that is used to reduce the error in reading of a binary optical encoder, is gray code. So why do we use gray code? Because gray code, the consecutive bits, they only have a difference of 1 bits. So only there is a change between change in 1 bits. And when we talk of any other code, that's octal, accessory, and BCD code, there is the change for more than 1 bits. So here we have example. So this is the decimal number from 0 to 8, and here we have binary, and here we have gray code, here we have octal code, here we have accessory code. So here we have binary. So this thing means as we go from 0 to 1 and 1 to 1 in successive bits, more than there is a change at more than 2 positions. So see here, there is a change at 2 positions. And let's see, let's have an example at this thing, octal. So here there is a change between more than 1 bit positions. Accessory code, here is a change, no, here is a change, accessory code 0, 1, yeah. So here is a change at more than 2 bits, 2 bit positions. But as we look at the gray code, the successive numbers, they only differ by 1 bit position, and as a result they are very less prone to the errors. So here you see there's only one bit change, here only one bit change, here only one bit change, here only one bit change, and so on. So this was a theoretical question. I don't think there will be any doubts, but still if there are any doubts in question 1 and 2, please ask. So the answer to this question was, let me just again show the answer to this question. So the answer to this question was, the code that used to reduce the error due to ambiguity in reading of a binary optical encoder is gray code, because there's only one bit position change, there's only change in one bit position in the successive numbers. Now question number 3, this is a true false type of a question. So the question 3 asks us, which of the following statements are false? Number 1, accessory code is both a sequential and self-complementary code. Number 2, in ASCII code, B is represented by 10010 and B is represented by 110010. Number 3, access code is 011 added to binary coded decimal. The allowed values are 011 to 0111 to 1111. Option 4, gray code is an animated code with a unit distance. It's also a reflected code, as by reflecting n-1 bit gray code, n bit gray code can be obtained. And number 5, binary to gray code as well as gray to binary code conversion uses XNOR gates. So I would like to ask this question to you. So which is the correct option to this question? So please read the question thoroughly and type in your answers, or you don't need to type in, but just take a look, and if you know the answer, please type in. Okay, I thought this was not asked. Okay, then there's no fun. Okay, but still, okay, what's the answer? Check it again. You have to say which of the statements are false. I'm afraid both of the options are incorrect, so let me just show you the solution. So the question asks, which of the following statements are false? So we have to mark the false statement. So the false statement is, accessory code is 011 added to binary coded decimal. The allowed values are 0011 to 111. So this part of the statement is correct, but this thing, the allowed values are from 0011 to 1100. So this thing, so this is false. And also this binary to gray code conversion uses XNOR gates. No, it uses XOR gates. So the conversion uses XOR gates, and the value here is 1100. So 3, and then all other statements are true. So 3 and 5 are incorrect. So option B is the right answer. I think you got confused with the true statements, that's why. So let's move forward to question number, this was question number 3 and now 4. So this is another true false question. So let me just leave the question for you, then I will ask you to answer this question, then after that I'll show you the solution. The accessory binary code is a self-complementing code because the binary sum of a code and its one complement is equal to 1111. It is a weighted code. Complement can be generated by inverting each bit pattern, the binary sum of a 2's complement and this 2's complement is equal to 1 1 1 1. So you have to find the true statements, the statements that are true statements that are correct. You need to find out those and tell me the correct answer. So this is question 4. So you need to tell me the correct answer to this question. So the question asks us which of the statements are true. I'll just read the question again. The accessory binary code is a self-complementing code because the binary sum of a code and its one's complement is equal to 1 1 1 1. It's a weighted code. Complement can be generated by inverting each bit pattern, and the binary sum of a code and its two's complement is equal to 1 1 1 1. Option A, you see two of the options are correct, 1 and 4, but 2 is not correct. Accessory code, is it a weighted or unweighted code? Just recollect that thing, then I think you'll be able to guess the correct, you'll be able to answer the right option. Accessory code, is it weighted or unweighted? So no, you just gave the correct answer. See, option A, 1 and 4 were right, but I told you this thing regarding weighted and unweighted code. So access3 is not a weighted code, it's an unweighted code. That means 1 and 4 are correct. 1 and 4 are correct, that means option 3 is the correct answer. That is option C. You can say C or 3. So let me just show you the solution. So we have a question that asks the accessory binary code is a self-complementing code because, so self-complementing code means it's the number, the binary number b1 and its complement b1 bar, their sum is equal to 1 1 1 1, and it is a self-inverting code because if you take the complement can be generated by taking by inverting the input bit patterns. Let's say the number was b1 was, let's say 0 1 0 1. Its complement is simply by inverting the binary bit position 0 1 0 1 0, and if you add those things, this is 1. And also let us have this accessory code b1 equal to, let me just b equal to, let's just say it is equal to 0 1 0 1. So this is accessory code. Okay, this is accessory code of number 2. This is 5, but accessory code of number 2. This is 5 accessory of 2, right? Decimal 2. Its complement, accessory complement will be 1 0 1 0. That is 8 plus 4 1 0 1 0. That is 8 plus 4 is 12. So the accessory complement of this number will be, okay, why I'm writing this? So its accessory complement will be b complement will be equal to 0 1 0. That is 4. No, that is 2. So 0 1 0, that is 2. Yeah. and if you add those things up, it will be equal to 1111. But I think we have to take 4-bit inputs, so we have to take like this. Let me just correct it. So we have to take, like, let's just say we have a number 1010, that is 8 plus 2 is 10. 8 plus 2 is 10, 5, x is complement 5, and its complement will be 0 1 0 1 0 1. So this thing will be its complement, and if you add them, it will be 1 1 1 1. So the accessory binary code is a self-complementing code, because the binary sum of a code and its complement is equal to 1 1 1 1, and complement can be generated by complementing each bit input bit pattern. So this thing will be equal to 4 plus 2 upon 5. Now coming to, I hope this was clear. Let me just check. So Kailash, was it clear? Okay, now let me just take a moment. I think I had a similar question related to this. I just wanted to show it, if I can find it. Just a second, if I can find it. This was question number 4. What did it be? Okay, I don't think I have it. I thought I had it. Sir, no any participant present here except me. Yeah, except you, there is no participant. Yeah, I know that. It happens with the increase in the, as we move forward to the lectures, the number of participants go down. In fact, in other lectures, my friend is taking this session in different lectures. Participants are also number of participants are also less. But I think this will help you whether you attend live session or whether you watch recorded videos. If you have time, you watch live sessions. So at live sessions, there is a one-on-one interaction, so you can ask doubts anytime. I hope these sessions are beneficial to you. Just a second, I think I had that question. Okay, now let's move forward to question number let's move forward to question number 5. So the question number 5 asks us, let me wait a second, I have to add a camera here first. So the question number 5 asks us, which of the following expression correctly matches the output z. So we have to find the output expression for z, and that correctly matches. So out of these 4, we have to correctly figure out which one of the which is the correct expression for z. So here we have 1 and here we have 0. So 1 goes to this thing, and then it goes to this thing, and finally goes to this thing. So it will be 1 when 0th selected, when this thing is selected, and when this thing is selected. So when select lines correspond to this position, when select lines correspond to this position, and when select lines correspond to this position, then only z is equal to 1. So z is equal to 1 when we have this thing. So when will be this selected? When a1, a0, b1, b0, when will be this selected? Is equal to 0, 0, 0. So this is here shown the configuration of the select lines at that position. So 0, 0, 0. Also this will be selected when this. So we can just figure out from this 1, 0, 1, 2, 3, 4, 5, 5. So z will be equal to 1 when a1, a0, b1, b0 is equal to 0, 1, 0, 1. 4 plus 1 is 5. And the z is equal to 1 when it's equal to 15th bit. a1, a0, b1, b0. So this is 1, 0, 1, 0. So if you carefully look at these things, so I forgot to mention this, a1, a0 is a 2-bit number and b1, b0 is a 2-bit number. So we need to find the relation between a and b from this circuit. So if you carefully look at this, the output is 1 when we have these 3 cases, and if you carefully examine these two individually in these 4 cases, you can figure out that the output is 1 only when a1 e0 is equal to p1 b0. So a1 e0 is 0, 0 and b1 b0 is 0, 0, 0. And here a1 e0 is 0, 1 and b1 b0 is 0, 1. Here a1 e0 is 1, 0 and b1 b0 is 1, 0. So that means z is equal to 1 only when a1 a0 is equal to b1 b0. So what does that mean? That means a is equal to b. So this circuit represents a equal to b, its output. So we will mark option C as our correct answer. So did you get it? Were you able to get this question? Okay. Was it also assignment? Was it also in assignment, or this was a new? Okay, that's fine. I don't want to repeat assignment questions. I did it in week 3 based on the feedback from the students, if you remember. But I found that that was not quite good practice to repeat the same questions, because you guys have that solved it and it's not interesting. That's why I come up with new questions every time. So now this was question number 5, if I can see at my screen. Yeah, now we have question number 6. So question number 6, this is an interesting question. We have these two 4-bit adders. So the above circuit adds two 4-bit accessory codes. So it adds two 4-bit accessory codes. The bits C3, C2, C0 are required to correct the sum after addition. So after addition, and these are function of C. So these 4 bits are function of C. So function of C means when C is equal to 0, they will add when C is equal to 1, they will add 3, and when C is equal to when C is equal to 0, they will subtract 3. So that's the condition on C. That's the condition on these bits based on the values of C. So we are required to find the expression for C3, C2, C1, C0 in terms of C on the parameter that on the bit that it depends. So we have C equal to 1, we add 3. So we add 3. Add 3 means C3, C2, C1, C0 will be equal to 0, 0, 1, 1, right? 3, because 2 plus 1 is 3. And C equal to 0 means subtract 3, that is minus 0, 0, 1, 1. But if you have to represent it in 2's complement, we can represent it as, so first we will take 1's complement, that is 1, 1, 0, 0, and we will add 1 to that, so that is 1, 1, 0, 1 in 2's complement. So this is in 2's complement, and this is also here. Because it's a positive number, we will just represent it by the number itself, 0, 0, 1, 1. So now we have, so we need to find the condition on C3, we need to find the expression for C3, C2, C1, C0 in terms of C. So C, when C is 0, we have to subtract 3. That means C3 will be 1, C2 will be 1, and C1 will be 0, and C0 will be 0 based on this. And when C is 1, we have to add 1, so this is 0 0 1 1, so we'll get this thing here. Now look carefully. So now look carefully individually these bits. So C3, what is C3 equal to? 1 0 1. What is C equal to? 0 1. So C3 is complement of C0, so C3 can be written as C bar, complement of C bar, sorry, complement of C. What is C2? 1 0, again complement of C, so C2 is again complement of C. What is C1? 0 1 0 1, following C, so C1 is equal to C. And what is C0? 1 1, so it's 1 irrespective of the value of C, so C0 is 1. So my C3, C2, C1 and C0 can be written as C bar, C bar, C and 1. So C bar, C bar, C and 1, and that's option 3. So my correct answer is option 3. Any doubts in here? Okay, I can, no issues. You can ask me anytime, to repeat any point anywhere. There is no issue with that. I'll repeat. So yeah, I will surely repeat. And also you have this advantage, sometimes if first of all I will repeat once twice, there is no issue repeating once and twice as long as your doubts are clear. So but even after that, because I have to cover some questions, even after that, but I'll repeat twice. There is no issue with repeating once and twice, but even after that you should go back to the videos, because videos are available and you can check them anytime. But I will repeat, there is no issue in repeating. I will repeat and I will teach it slowly, no issues. So this was question number 6. I have to repeat it again. Yeah, I'll repeat from start. So we have two full bit adders, and the above circuit adds two 4-bit accessory codes. So accessory codes are added. The bits C3, C2, C are required to correct the sum after the addition, and these function of C. So based on the function of based on the value of C, it will correct the this thing. So D3 will be correct. D3, D2, D1, D0 will be the corrected addition of these two accessory codes. So what is happening? If C is equal to 0, we have to subtract 3. If C equal to 1, we have to add 3 for the correction. So when C is equal to 1, we will add 3. So add 3 means C3, C2, C1 and C0 will be 0 0 1 1, because the number is positive, so it will be 0 0 1 1. And if C is equal to 0, we have to subtract 3, so that means minus 3, and minus 3 into 2's complement can be written as, we will take the 1's complement of 0 0 1 1, that is 1 1 0 0, and then we will add 1, so that will be 1 1 0 1. So I got two conditions. For C equal to 1, I have C3, C2, C1, C0 as this, and for C equal to 0, I have C3, C2, C1, C0 like this. So my C3, C2, C1, 0 0 and C1 0 I have written here. So 1 1 0 1 when C is equal to 0 here, and 0 0 1 1 when C is equal to 1. Now check. Now I'll check C3. C3 is 1 0 when C is 0 1. That means C3 is complement of C. That's what I have written here. C2 is 1 0. That is C was 0 1. That is C2 is again complement of C. C1 is 0 1 when C is 0 1. So C1 is equal to C, and C0 is 1 irrespective of the value of C. So C0 is 1. So that means my C3, C2, C1 and C0 will be written as C bar, C bar, C and 1, and that is option 3. I hope it was clear. Anytime you have any doubts, please ask. I'm just giving you time, you ask. Even while I am doing the question, you type it in the chat box. I'll just check the chat box and I'll answer to your queries. Now question number 7. Question number 7 asks us the gray code of 567 and B74. So 567 is in octal. So see, sometimes this is just a tip whenever you are solving MCQs. So sometimes in a rush you'll forget these bases. So you'll consider either both of them at 8 and both of them at 16, and you will do solve question. And the question, the people that are making these questions, they are quite smart, and they'll put options like that only. So you think you have done it correctly. So always read the question twice. So here the number is octal, and here the number is hexadecimal, and we need to find the gray codes of both of them. So first we'll take 567. So this 567 is in octal, so octal to binary, you know that how we convert. We'll take one digit and write its 3-bit equivalent. So 7, its 3-bit equivalent is 1 1 1. Then 6, its 3-bit equivalent is 4 plus 2 is 1 1 1. 4 plus 2 is 6, 1 1 0. And 5 is 1 0 1, right? This is its binary form. Now we have to convert this number into its gray code. So gray code of any is converted by this formula, bn minus 1. So gn minus 1 is equal to bn minus 1 XOR with bn. So g0 is equal to b0 XOR with b1. G1 is equal to b1 XOR with b2, so on, and finally gn last bit is equal to the binary bit. So here we'll take XOR. So g0 is equal to b0 XOR with b1, so we'll take XOR of these two. 1 XOR with 1 is 0. Then b1 1 XOR with 1 is again 0. Then b2 1 XOR with 0 is 1. Then b4 is b0 b1 2 3. Then g3 will be 0 XOR with 1, that is 1. Then 1 XOR with 1, that is 0. Then 1 XOR with 1, that is 0. Then 1 XOR with 0, that is 1. Then 0 XOR with 1 is 1. And 1 2 3 4 5 6 7 8 3 6, and finally it will be 1. So this is 1 1 1 0 0 1 1 1 1 0 0 1 1 0 0, and we have to write the answer in octal only. So this is 7, this is 1, and this is 4. So it is 714 in 8. And also now we have this gray code. So if you want to convert this gray code into I'll just show it after that. Now B74, this B74 is in hexadecimal system. So B74, so this B74 can be converted into binary by taking each digit and writing its 4-bit equivalent. So it's 0 1 0 0 for 4. For 7 it's 0 1 1 1, and for B is 9 10 11. B is 11, so that is B is 11, so that is A B C D. B is 11, yes. So 8 plus 2 plus 1, so 1 0 1 1. 8 plus 2 plus 1. And similarly we will convert its what should I call it, gray code. So this is 0 XOR with 0 is 0. 0 XOR with 1 is 1. 1 XOR with 0 is 1. 0 XOR with 1 is 1. 1 XOR with 1 is 0. 1 XOR with 1 is 0. 1 XOR with 0 is 1. 0 XOR with 1 is 1. 1 XOR with 1 is 0. 1 XOR with 0 is 1. And 0 XOR with 1 is 1, and then 1. So 4 4 and 4. I have done it right. Yeah, 1 1 1 0 1 1 0 0 1 1 0. So it is 8 plus 4 is 12. 12 plus 2 is 14. So that is E. And this is 1 0 0 0 1. So 1 1. So this is 1 1 1 1 0 0. 8 plus 4 is 12. So that is C. And then finally we have E. So this is in ECE. So this is 16. So 748A, 8 in octal, and ECE in hexadecimal. And now if we have a gray code like this, gn minus 1, so on up to G1 and G0. And if you want to convert into binary, so what we'll do, we'll just put it this bit MSB here. MSB of gray code is equal to MSB of binary code. Then we will XOR with this, that thing will come here, and that thing will be XORed with this, so on. This is B1, that thing will be XORed with this, and finally we have the B0. B1 XOR with G0 will give us B0, and so on. So did you get it? Okay, now we'll just move forward to question number, this was 7, and now we have question number 8. So the question number 8 states that the output Y of a 2-bit comparator is logic 1 whenever 2-bit input A is greater than 2-bit input B. So it says that the output of a 2-bit comparator is logic 1 when A is greater than B, and the number of combinations for which output is logic 1 is, so we need to find out the number of combinations for which the output is 1. So output is 1 when A is greater than B. So a 2-bit number A greater than 2-bit number B, that implies my output is 1, and we need to find out the number of possible combinations for which my output will be 1. So a 2-bit number A as A1, A0, and a 2-bit number, another 2-bit number will have B1 and B0. So when is A greater than B? When A1, when A is 1 1 and B can be 0 0, 0 1 and 1 0. So when A is 1 0, so when A is 1 0, A can be greater than B when B is 0 0 and B is 0 1, and when A is 0 1, A can be greater than B only for 0 0. So these are the number of combinations for which my output will be equal to 1. So how many possible cases? 1 1 0 0 is 1, 1 1 0 1 is 1, 1 1 1 0 is 3. So here I have 3, here I have 2 combinations, and here I have 1 combinations. So in total how many combinations I have? 3 plus 2 plus 1. So for 6 combinations my output is 1. So my answer is 6. So there is another general formula through which you can calculate this thing. So that formula says that for an n-bit comparator, so the number of possible combinations for a number A greater than B are 2 to power 2n minus 2 to power n by 2. So here n was 2, so 2 to power 4 minus 2 to power 2 by 2, right? And 2 to power 4 is how much? It's 16. 16 minus 4 by 2, and 16 minus 4 is 12, and 12 by 2 is 6. So this is a more general thing, or you should call as some. Now this was question number 8. Any doubts? Sir, have you any other to convert binary to gray code? No, there is only one thing. You have to take XOR. I'm not aware of any other method. There might be, I'm not aware. You just have to take binary of those. I don't know whether in my bachelor's days was there any other method I have done. I don't remember. There might be any, so you can check up. So if I find out, if there is any other method, if I find it, I'll let you know in the next lecture. But right now I'm aware of this method only. So this was question number, what was this? Question number 8. Now question number 9. So question number 9 asks, for the divider circuit shown below, so the divider circuit that is shown here, find the input bit arrangements for the last row of divider unit cells including first 0. If the input is D, so the dividend is this and the divisor is this. So this we have this array based divider circuit, and we need to find out the this row, contents of this row. So before we move forward in solving the question, I just like to show here this thing. This is a unit cell. You might have seen it in your lecture. This is a unit cell. Here we have inputs X and here we have input Y. Then we have output. Here I have output B out, and here I have output B in. What it has inside it has a subtractor, full subtractor, so X Y, which takes input B in, and here I have B out, and then I have a multiplexer. This is 1, this is 1, this is 0, and we have a select line, and we have output. Here this S is B out complement, right? So this is the unit cell in this. Here are my dividends bits: D6, D5, D4, D3, D2, D1, D0, and here are my divisors: D0, D1, D2, D3. So we'll just move forward and solve this thing. First let me just write D here. I'll just introduce a new slide first because it will take up a lot of space. So let me just use a new slide, and then we can proceed. So my divisor is, I'll just write the divisor here. D is 4 1 4 1 and 0 1 0 0 1 0 0 1 0. Yes, and my dividend is 1 0 1 0. Okay, this is the all information we need. Other than that, we can proceed. So I'll just use different colors to separate the divisor, dividends, quotients and all. That will be helpful for us. So I'll just write down my dividend first, that is D0, D6, D5, D4 and D3. Here I will write down D6, D5, D4, D6, D5, D4, D3, D2, D1 and D0, right? Now I'll write down the divisors. The divisor is 1 0 1 0, that is 1 0 1 0, and now I'll do the subtract operation, and subtract operation I'll just write in green ink. So you need to remember this full subtractor operation to do the subtraction operation here. So here the input being is 0, so 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 0 is 1, and 1 minus 1 is 0. So my B out will be 0, its complement will be 1. So when complement is 1, the subtraction result is selected. So my below row will be that I will write in black. So I have to select these results of subtraction. So it will be 0, it will be 1, it will be 0, and it will be 1, right? Now I will write down the divisor. So my divisor is 1 0 1 0, and here I have 0, so that thing comes from here. I'll just show you from it comes from here. See, it comes from here, so it is 0. And now I'll just do the subtraction operation. So this 0 minus 0 is 0, B in was 0, 1 minus 1 is 0, 0 minus 0 is 0, 1 minus 1 is 0, 0 minus 0 is 0, my output is 0, and again the subtraction result will be selected. That thing I will write down in black. So So where's my pen? Something happened to my mouse. I'm not able to get the control of it. Yeah, it happens sometime. So pointer options pen, so I'm not able to get it. Just a second. Okay, now again the input is 1. We have to select the subtraction result. So it is 0, it is 0, it is 0, it is 0, and it is 0. And now we will write down the, so here this will not come here because this is not here and there is nothing here. So here now I'll just write the divisor. I'll just change the ink color. So my divisor here, it will be 1 0 1 0. Here this will be 0 coming from this, and now I'll do the subtraction operation. So 1 minus 0 with being 0 is 1. 0 minus 1 is 1 with borrow 1, so it is 0 minus 0 with being is equal to 1, so it will be 1. It is 0 minus 1, this will be 0, and this is 0 minus 0 with being equal to 1, it will be 1. So this is 1, so the B out, it will be 0, and here the inputs will be selected, so it will be 1. Here inputs will be selected, so where am I? 0 0 0 1 0 0 0 1 1 0. So inputs will be selected, so this is 0, this is 0, this is 0, this is 0, and this is 1. And here I will have another 0. Here I will have divisors. Here I will have divisors 1 0. I have written this thing here. This thing is not there. So this is here. This let me just correct it. So this is not here. So this row will be, let me just use a black pen here. This will be 0, this will be 0, this will be 0, and this will be 1, and we have this 0. I'll just plug it here only. And then we will write down the divisor. That is 1 0 1 0, and here this is 0. So this is my answer, because it was asking input to the last row, but we will also solve it completely. So I'll just write down the subtraction result. So 0 minus 0 is 0, 1 minus 1 is 0, 0 minus 0 is 0, 0 minus 1 is 1 with borrow out as 1. So 1 minus 0 minus 0 is with being as 1, it will be 1, and my output will be 1, and that complement will be 0. So this is my quotients, 0 0 1 1. These are my remainders, and my final row is 0 0 0 1 0 0 1 1 0 0 0 0 0 1 0 0 1 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 1 1 0 0. So option C is my correct answer. So this we need to figure out. So option C was my correct answer. So did you get it? So question number which was this? Question number 9. Now we can move forward to question number 10. So I'll just read this question for you, and you'll do it first, then I'll show you the solution. 2-bit numbers A1, A0, B0, and two 2-bit numbers A1, A0, B1, B0 are given as inputs to a 2-bit comparator. The comparator outputs are P, Q, R. Then for the circuit shown below, the probability that S2 equal to 1 is, so you need to find out the probability that S2 equal to 1 will be. So just find out. I'll again read the question. We have two 2-bit numbers A1, A0 and B1, B0. They are given input to the 2-bit comparator. The comparator has outputs P, Q, R based on the condition A less than B, Q is A greater than B, R is equal to B. Then you need to find out what is the probability that S2 will be equal to 1. So do it. I'll give you 5 minutes. So after 5 minutes, I'll just show you the solution. So we have a new participant here, so let me just update him. So we have a new participant here, and let me just update the person what we are doing right now. So we have question number 10. So the question number 10 is two 2-bit numbers A1, A0 and B1, B0 are given as inputs to a 2-bit comparator. The comparator outputs are P, Q, R. So P is equal to A less than B, Q is equal to A greater than B, R is equal to A equal to B. So then for the circuit shown below, the probability that S2 equal to 1 is, so I'll be just giving you a couple of minutes to solve this question, then I'll just give you the solution. So try this. Have you done it? I'll just wait for a couple of minutes, and then I'll just show you the solution. So that's a good thing. If you are not able to solve, you will just learn a new thing today. Not new thing, everything is same. So where is the problem? So I'll just show you how to approach this problem. So uh, the purpose of live session is this only, to get acquainted to a new set of problems and how to approach a problem, so that will help you in, with your exams in future. So I'll just show you how to approach this problem the way I approach it. So I have outputs. So this is a 2-bit comparator and its outputs are P, Q, R. A less than B, A greater than B, and A equal to B, right? So these are my let me just check whether I have turned on my mic or not. I'm not sure. Yeah, I turned on my mic. So these are my outputs of a comparator, right? This thing is pretty trivial and there is nothing new. Then the output, these three are given to a decoder, 3:8 decoder, right? And its outputs I have 8 bits from S0 to S7, right? So S2 is the third bit and it will be selected. When will S2 be equal to 1? First of all, that's the required goal. When will S2 be equal to 1? Forget about combinations, just consider this part only. If it was a decoder only, when will S2 be equal to 1? So I'm asking this question to you. Let me just have a one-on-one interaction with you regarding this question. So when will S2 be equal to 1? Kailash, you there? So when will S2 be equal to 1? Just recollect your thoughts regarding a decoder. So when will S2 be equal to 1? It will be equal to 1. Now let me show you. It will be equal to 1 when P is equal to 0, Q is equal to 1, and R is equal to 0. So that is PQR is equal to 0, 1, 0, right? So 0, 1, 0. Now forget about decoder. Now consider only comparator. So my output is 0, 1, 0 of a comparator. So I'm just saying comparator output should be equal to Q, that is A greater than B. So I have found out a condition. My S2 will be equal to 1 when A is greater than B, right? So when will be A greater than B? When A is equal to 1, 1 and B is equal to 0, 0, 0, 1, 1, 0, and A is equal to 1, 0 and B is equal to 0, 0, 0, 1. When A is equal to 0, 1 and B is equal to 0, 0. So there are 6 possible cases for A and B for which Q will be equal to 1, which ultimately will have S2 equal to 1. So 6 possible cases out of how many possible cases? How many possible cases are there? There are 16 possible cases. 2 to the power 2n. 2 to the power 2 into 4, 16. You can also have it like this. So 1, 1 will have a comparison with 0, 0, 0, 1, 1, 0, 1, 1. So these are 4 and these are 4 times. So 4 times 4 is 16. So there are total 16 cases and 6 are our favorable outcomes. So the probability S2 equal to 1, let me just write it down. P2 S2 equal to 1 is 6 by 16. How much is 6 by 16? 6 divided by 16, it's 0.375. So the correct answer was 0.375. So whenever you find these questions, try to break it. Find the condition, then go. Okay. Did you miss any part? So did you get the solution, or should I repeat? Yeah, I'll just repeat it quickly because we have to solve other questions. But so I was just asking, break it. So when will S2 will be equal to 1? So my initial question to you was, I think there was some connection issues with you. So my initial question was, when will S2 be equal to 1? When will S2 be equal to 1? S2 will be equal to 1 when P is equal to 0, P is equal to 0, Q is equal to 1, and R is equal to 0, right? So now taking comparator case, that means A greater than B, Q, because of Q is equal to 1. So when will A will be greater than equal to A will be greater than B? So there are 6 possible cases when A will be greater than B. We also saw it in the previous question when we calculated that. Here there are 6 possible cases, right? Now 6 are my favorable outcomes. But what are the total number of outcomes? So I can have 0 0, it will be compared with 0 0 0 1 1 0 1 1, and similarly there are 4 and it will be 4 times 4, so there are 16 possible outcomes. So my probability will be 6 by 16, that is 0.375 favorable outcomes by total number of outcomes. So did you get it? Try to break the problems, just see what the question is asked and how we can is asking and how we can approach that. So now coming forward to question number, this was 9 and now 11. So find the 12-bit Hamming code for a given 8-bit data word. So 8-bit data word is my D7, D6, D5, D4, D3, D2, D1 and D0 are 1 0 1 0 1 1 0 0, something like that. I just messed up. 1 0 1 0 1 1 0 0, yeah. So in the 12-bit Hamming code, how is it written? It's written as P1 is my first parity bit, then I have P2 my second parity bit, then I have D1, D0, then I have D, should I call it D0 or D8? D1, let us term it as D1. This is 8 7 6 5 4 3 2 1 0. Let's just term it as, forget this thing. So our 12-bit Hamming code can be written as P1 P2, then P3, then D2 D3, then D4, then P4, then D5 D6 D7 and D8. Forget this thing, huh? So these are my parity bits here. Now I'll just mark the bit position on 2 3 4 5 6 7 8 9 10 11 12. So what will P1 be equal to? P1 will be equal to all data bits in which bit position at 1 is 1. So if you write the 8 4, what I mean to say, if you write a 8421 syntax, so this is 0 0 0 1 0 0 1 0 0 0 1. So this is 1 2 3. So this position, I mean to say, wherever there is 1, it's 1 3 5 7 9, or in odd positive integers. So 1 is the parity itself, so we'll write 3 5 7 9 11 XOR of these bits. So it's XOR of 3 5 7 9 11. So 3 5 7, so let me just write the bits here. So it is 1 1 0 1 0, then 1 1 0 0. So XOR of 3 5 7 9 11. So XOR of 3 5 7 9 11 is XOR of 3 is so here 3, this 3 5 7 9 11. So XOR of 1 0 3 5 0 7 9. What is 9? 1 and 11. So this is XOR of, it will be 0. So P1 will be 0. So here I'll write down 0. I'll just use new color for it. So it is 0. Then P2 will be equal to wherever there is 1 in the second bit. So it is in 3 6 7 10 and 11. So it will be XOR of 3 is 1, 6 is, so 6 is here, 1 2 3 4 5 6, 6 is D3, D3 is 1, 7 is 0, 10 is 1 and 11 is 0. So it will be equal to 1. So P2 will be equal to 1. Then we have P3, that will be XOR of, now I'm just skipping the steps because now you got an idea what to do. 5 6 7 12, and if you carefully get the bits at this position, my answer is coming out to be 1. So my P3 will be 1, and finally my P4 XOR of 9 10 11 12, that is 1 1 0 0, that is 0. So my P4 will be 1. So my final number will be 0 1 1 0 0 1 1 0 1 1 1 0 0. So 0 1 1 1, so 0 4 1, so 0 3 1. So this thing 0 3 1, 0 1 0 1 and 1 1 0 0. So option B is my correct answer. I wrote it in a slightly shabby manner, but I think you got an idea. So no, if you have any issues with question number 10, I can repeat. Any doubts with question 10? We can comment. We can discuss it at the end. What about 11? Any doubts with 11? Question number 11. So now question number 11 was clear. So now question number 12. So we have a question. A 12-bit Hamming code read from a memory location. This Hamming code contains 8-bit data and 4-bit code word. What was the original 8-bit data stored in the memory location if 12-bit Hamming code is this? So we have to find the position at which the error occurred, and then we have to find out the correct code. So we can write it like down this. So let me just write down this 1 2 3 4 5 6 7 8 9 10 11 and 12. So my received code was 1 1 0 1 0 1 0 0 1 0 1 0. Now find the check bits. So C1 will be equal to XOR of bit set positions 1 3 5 7 9 11. so this will be 1 XOR of 1 0 0 0 1 1, so it will be 1. C2 is equal to XOR of 3 2 3 6 7 10 11. it is 1 0 1 0 1, so this thing is again 1. Then C3 is equal to XOR of 4 5 6 7 12. so this will be 1 0 1 0 0, so it will be 0. Then we have C4, that will be XOR of 9 8 9 10 11 12, so that will be again 0. so the error will be at bit position C4 C3 C2 C1. so this is actually like this: C8 C4 C21 C8 421. so error will be at position 0 0 1 1, going like this. so this is 2 plus 1 3. error will be at bit position 3, so that is 1 2 3. so error will be at position 3. so if it was 0, it will be 1. so my correct code will be 1 and 0 1 0, then 1 0 1 0. my correct code will be 1 0 1 0 1 0 1 0. so option A is my correct answer. so was this question clear? Any doubts? Okay, that's nice. Now question number 13, I would like you to do it first and then I'll just show you the solution. so it says that in Hamming code, how many check bits are required for data word of 25 bits? so you need to find out the number of check bits required for 25 bit data word. you first do it, then I'll just show you the solution. I'm afraid this is incorrect. I'll just show you the solution. So in a Hamming code, so we need to find out the number of Hamming bits, this check bits. So let's just say there are k check bits in a Hamming word, and so we have this condition: 2 raised power k should be greater or equal to n plus k plus 1, where k, as I already defined, are number of check bits and n is the number of bits in a data word. So here n is 25, so 2 raised power k should be greater than 25 plus k plus 1. So 2 raised power k should be greater or equal to 26 plus k, right? Now we'll do some guesses. Let's just say k is equal to 4, so 2 raised power 4 is 16. 16 should be greater or equal to 26 plus 4, that is 30. 16 greater or equal to 20, so this doesn't satisfy. Now we'll just put k equal to 5, so this was for k equal to 4. Now we'll just put k equal to 5, so 2 raised power 5 greater or equal to 26 plus 5, so 2 raised power 5 is 32. 32 is greater than or equal to, so 32 is greater than 31, so this condition is satisfied. So that means k is equal to 5. So the number of check bits required for a 25-bit data word is 5. Now moving forward to the next question. This next question is also based on this logic that we did here. So here, what is the size of Hamming code for a 32-bit data word? So here we need to find out the complete size of a Hamming code, that is n plus k. So we know, let's just say there are k check bits in a Hamming code. So the condition that it should satisfy is 2 raised power k should be greater than n plus k plus 1. And here n is 32. 32 plus k plus 1. So 2 raised power k should be greater than or equal to 33 plus k. So we know that 2 raised power 5 is 32, so 5 can't be there, it will be 6. So 2 raised power 6 is 64. 64 is greater than 33 plus 6, that is 39, right? So the total number of bits will be k is equal to 6. Total number of bits will be equal to n plus k, the size of Hamming code, and n is equal to 32 and k is equal to 6. 32 plus 6 will be equal to 38. Got it? Were you aware of this criteria? 2 raised power k should be greater than or equal to n plus k plus 1. Okay, you can just check it. You can just refer the lectures. If not, you can just refer to some other source, maybe book. It will be there. So the next question will be question number 13 version, 14 version, 15. Yeah, this is an interesting question. So question number 15, it has, we have an ALU unit. So here is an ALU unit whose output is, if s equal to 0, so the select line is equal to 0, y0 will be NAND, y1 will be NOR of a and b. If s equal to 1, y0 will be a complement b plus ab bar, y1 is equal to ab. So this is a sum bit of a half adder and carry bit of a half adder, like that. Now this ALU unit is taken and it's cascaded like this. So ALU unit is taken, and here a is equal to s, and here y0 is equal to x, and we need to find out the result as z0 z1 in terms of a and b. So how will we do it? We'll first just write down the condition for a single unit. Let's just consider this. So when s equal to 0, y0 is equal to ab complement, and when s equal to 1, y0 is equal to a complement b plus ab complement. So y0 can be written as s complement a b complement, right? So that means s equal to 0, y0 will be a b complement plus S A complement B plus A B complement. So this I wrote down a condition for my y0, and similarly y1 will be equal to S complement A plus B complement plus S A B, right? This will in fact be written like this: S complement A plus B complement can be written as, using the help of De Morgan's law, S complement A complement B complement plus S A B. Now here for let's just consider this y0 of the below circuit. Y0, here S is equal to A. First things first, S thing is equal to A. This S is equal to A. So we'll just replace this S by A. So we will have y0 will be equal to A complement, just plugging these value here, A complement, then AB complement as it is. Then in place of S I will just write down A, and I'll write down A complement B plus AB complement. So this thing is, so this will be A complement, and this thing will be A plus B, A complement plus B complement, and this thing will be A complement will be 0, and this will be A B complement. This thing will be A B complement. No, let me just check it. Something is missing here. A B complement, A complement. This is A complement. This thing is A complement B, that is 0, plus A B complement, and this is A complement plus A complement B complement plus A B complement. This is A complement plus B complement will be taken out. This will be A plus A complement is this is A plus A complement will be 1. So this is A complement plus B complement, and this is A complement plus B complement. So A complement plus B complement is simply A B complement. So this is my y0. I'll call it 1, and my y1 will be equal to S replacing S by A. So this is y1 will be equal to A complement B complement plus A B. So it will be simply equal to A complement B complement plus AB, right? So these are my outputs here, y0 and y1. Now this goes to input to another ALU where S is equal to y0. Now I'll just introduce a new slide here. And we will continue here. So I'll just write down the from results from previous slide. Y0 is equal to AB complement, and y1 is equal to AB complement plus A complement plus AB. Now Z0 will be equal to replacing S by y0 for this ALU. So my y0 Z0 will be equal to Z0 will be equal to y0 complement y0 complement with y0 y1 bar plus y0, that is with y0 complement y1 plus y1 y0. So my z0 will be equal to y0 complement, and my y0 will be equal to something I am missing here, y0 complement plus y1 complement, it will be equal to y0 complement plus y0 y1 complement. Here it is y0 complement y0 and y0 0. Let me just check it. I am just missing something. Let me just check it. One minute. Oh yeah. Let's see here where I messed up. See, forget about this thing. This is also another way of doing it, but it will elaborate your this thing. So we got this thing, y0, this thing and this thing are similar, just the inputs are different. So here inputs were a and b, so y0 was equal to ab complement, right? We got it here. See, so if yeah, so y0 is equal to ab complement, right? So that implies z0 is equal to y0 y1 complement. So using this I would have also gotten the answer, but it was a more elaborative way, because I was just again doing these steps and with more number of inputs, I mean to say variables, so this will mess up. But we had this result, we can use it. So this thing and this thing are similar, so that means z0 is equal to y0 y1 complement, right? And y0 is equal to, let me just write it, y0 is equal to ab complement, right? ab complement, and y1 is equal to ab complement plus ab, a complement b complement plus ab. This is y0, this is y1, and we have a whole complement, right? And then we have z0, so we will use De Morgan's law, a complement dot a dot b का whole complement. So this is a b complement plus complement of this thing, right? That implies z0 is equal to ab. This is OR gate, no sorry, XOR gate and XNOR gate. So XNOR gate's complement is XOR gate, so it will be a complement b plus a complement b, right? And here I will just take b common, so it will be a plus a complement plus a complement b. Finally it will be b plus a complement b, b plus sorry, a plus a complement b plus ab, b plus ab, it will be, so let me just write it here. So z0 will be equal to, I have ab plus a complement b plus a b complement, so this will be b plus a complement b, taking b common, and we know this a plus ab, a complement b is equal to a plus b. Here a is equal to b, so it will be a plus b. So z0 will be equal to a plus b. Z naught will be equal to OR operation. Now we need to see what will be this thing equal to Z1. So now Z1 will be equal to y0 y1 complement plus y0 y1 using this result, and y0 is equal to ab complement and this complement, and y1 is equal to ab plus ab, and then we have complement, then we have plus ab complement for y0, and y1 we have a complement b complement plus ab. Now z1 will be equal to ab whole complement will be equal to ab, and this will be again equal to XOR this thing. This thing you can break it like this: a complement plus b complement using De Morgan's law, and inside you will just write it like on this. So why I'll break it, I'll just show you, because a complement so a complement this is a complement b complement b, yeah. So I'll just write down like this. So this is a b, and when we multiply it by a complement this will be 0, and when we multiply it by b complement this will be 0. So nothing comes out from here, so only things that will coming out will be from here, that is a complement b complement plus a complement a b will be 0 plus b complement a, so it will be a complement b complement plus 0. So I am finally getting a complement b complement, so this thing is equal to a plus b ka whole complement. So this is NOR. So my z0 was OR, my z1 is NOR. So my z0 was OR and my z1 is NOR, so option A was correct answer. So here this thing that I had done, this was just increasing my it was just elaborating the things, and it was not helpful. So we just took the help of these results that we got for this unit, and just applied the results for the second unit. So option A is the correct answer. Now coming to the question 16. So we have an ALU, which of the following expression is correct? So we need to find out the expression. If you see, we need to find out the expression, all of the inputs. So we need to find out the expression for y1 when Cin is equal to 1. When Cin is equal to 1, we need to find out the expression. So we will just draw the K map for this thing. So in lecture you have done it for y0, now we will do it for y1. So here I will write down S0 S1 S1 S0 complement, then it is S1 complement S0, then it is S1 S0, and then finally we have S1 S0 complement. Here I have a complement b complement, a complement b, then a b, and this is a, these are 1 1 1 1 1 1 1. So when S1 is 0 0, we have no conditions, we have a b complement, so this will be all equal to 1. And when we have a plus b complement, so that is a complement b complement, so this will be 1. And for this thing 1 1, we have a plus b, so for a plus b we have this thing. And when we have 1 1 1, okay, this was this thing, a plus b plus 1, so this is a plus b plus 1. And for 1 1 0 and for 1 0, so we have 1 0, we have a plus 1, so and for that thing I will have these two. So we will just use the K map. We will use have this chord, this pair, and this is the individual minterm. So my expression will be equal to term coming out from this thing is a complement b complement for a1 b1. I should write a1 b1, and then they have this chord, so it will be s0 complement a1 complement. Then I have this pair, for that it will be s1 complement s0 complement b1, and I have this min term, for it will be s2 s1 s0 a1 b1. So a1 b1 complement plus s0 complement a1 complement plus s1 complement s0 complement b1 complement b1 complement, and then s0 s1 a1 b1. So option B is the right answer. Now question number 17. So I want you to do it, but here I have to make a one correction. So this is 0 1 0 1, this is 1 0 1 0 1 0. Read it like this. No, I don't think we have time. Let me just show you the solution. So we have these four. An error correcting code has the following codes: 0 0 0 0 0 1 1 0 1 0 1 0 1 0 1 1 0 1 0 1 0 1 0 1 0 and 1 1 1 1 0 0. What is the maximum number of bit errors that can be detected and corrected? So if you carefully examine these four code words, the minimum Hamming distance between 0 0 and 0 1 1 0 0 is 4. You can just try it for yourself. And we know that d min is equal to b plus 1 for the number of bit errors. So this is bit error, so d min is equal to 4. This is b error plus 1, so b error plus 1 is equal to c. So the number of maximum number of bit errors it can have is 3, and for the maximum number of bit errors it can correct is twice b plus 1 is equal to d min. So twice b is equal to 3 minus 1. So twice b is equal to 3, twice b plus 1 is equal to 3, d min twice b is equal to 2, b is equal to 1, b is equal to 1. Oh, this is 4, 4 minus 1, this is 3, so 2b is equal to 3, that implies b is equal to 1.5. So the maximum number of bit errors it can have is 3, and maximum number of bit errors it can correct is 1.5. So option B. Now this question, this is the final question of today's lecture. So in the circuit diagram given below, if b is equal to 0 1 0 1, so b is equal to 0 1 0 1 and y is equal to 1 0 0 1, find the value of a, b and c. Find the value of a. The values of a and y are in accessory code representation. So if you carefully examine this thing, we had looked at this thing earlier. This is simply a accessory code adder. So here two accessory codes are added, and here the correction is done. So see, we did a question earlier. So what is this? C complement C1, right? If you remember. So here C is C3, so these things go here. C complement, here C. So this is the correction part, and here we have the result of the addition, and finally we have the correct code. So this thing is an accessory addition. So accessory addition of a plus b. This is a circuit of a subtractor of a plus b. So for b, accessory code is 0 1 0 1. So this is 4 plus 1 5. That means this is a accessory code of 2. And finally we have output equal to 1 0 0 1. That is 9. That is accessory code of 6. So y is equal to a minus b. So y plus b is equal to a. So a is equal to 6 plus 2, that is 8, and its accessory code representation will be 11. So 11 in accessory can be written as 8 plus 4 is 8 plus 2 plus 1. So 1 0 1 0. 1011, sorry, 1011, because 8 plus 2 is 10, 10 plus 1 is 11, so this is 11. So what I did, this is the circuit for an XS3 subtractor. So A minus B, and we have this result that is in XSB code. So for getting the A, I did y is equal to y, A is equal to y plus B, and that is 6 plus 2 is 8, that is 6 plus 8 plus 6 plus 2 is 8, yeah, 6 plus 2 is 8, and 8's XS3 is 11, 11 in binary will be 1011, so this is my answer, option A. So earlier on, I think you had some queries regarding question number 10. Let me just show you question number 10 again. So we have 2-bit numbers A1 A0, A1 A0, and 2-bit numbers B1 B0. They are given to a comparator, and we have the outputs of a comparator PQR as A less than B, A greater than B, A equal to B respectively. The comparator outputs are PQR. Then for the circuit shown below, the probability that S2 equal to 1 is, so S2 is the one of the output bits of a decoder. So when is S2 equal to 1? S2 will be equal to 1 when PQR are 0, 1, 0. That means Q is equal to 1. When is Q equal to 1? When A is greater than B. So when will A be greater than B means a 2-bit A number A is greater than 2-bit B number. So when is this possible? There are 6 possible cases: when A is equal to 1, 1, when A is equal to 1, 0, and B is equal to 0, 0, 0, 1, when A is equal to 0 and B is equal to 0, 0. So there are 6 possible cases, 6 possible cases. And how many total possible cases are there? There are 16 possible cases, that is 6 by 16, and that is 0.375. That's what I have done here. So question 15 is a lengthy problem, sir. Let me just check what is question 15 again. And I'm not aware of that thing, hall ticket and when we will receive hall ticket. I'm not aware of that thing. You need to contact the team members. My job is to teach this live sessions and all. You can ask them, or there will be in notification, I think there will be these dates will be communicated to you, but still you can mail them anytime and have your doubts cleared. So question 15 is lengthy. Question 15 is lengthy. Where is question 15? So actually, see, this was not lengthy because I made this step that was wrong. I didn't require to do it. I would have done it if, see, you could have done it. First you write down the expressions for y0 and y1, and then you plug those values here. So this thing was done quickly, right? y0 equal to ab complement, and y2 equal to a complement b complement ab, right? This thing was done quickly. Then what is z0 z1? Let's just say we don't have first thing connected to it. Z0 would, but we know z0 will be equal to y0 y1 whole complement, and z1 will be equal to y0 y1 plus y0 complement y1 complement. Then yeah, this part is bit tricky. Here you need a good this thing intuition expertise. Let's see what I did here for z0. Where is my z0? Yeah, z0 is equal to y0 y1 complement. So y0 is ab complement and y1 is ab complement plus ab. So then I use De Morgan's law. I know that complement whole complement is number itself. So sorry, the this ab equal itself, and then I know this is a complement b complement plus ab. You know this is XOR gate. So XOR gate's complement is XOR gate. A complement b plus a complement b plus ab complement. So this should be ab complement. So ab plus a complement b plus ab complement. Then I took b common. So a plus a complement is 1. So this is b, and ab complement, and we know that b plus ab complement is simply ab, right? So this thing was done pretty quickly. And for z1 I have y0 complement y1 complement plus y0 y1. Now I have ab complement whole complement, so this is ab, and here I have again XOR complement, that is XOR a complement b plus ab complement. So see how to do things quickly. A and a complement is 0, so don't care about other terms. B and b complement is 0, so don't care about other terms, right? And also I had this thing here, ab complement. So that thing I use with the help of De Morgan's law. I wrote a complement plus b complement, and here I have a complement b complement plus ab. So see, a complement b complement, right? A complement b complement, a complement a 0. Whenever you see a complement and a input and its complement coming out together, it will be equal to 0. Don't care about any terms. B complement A complement B complement, so it will be equal to A complement B complement, and you see and B complement, write 0. So only two terms are left, A complement B complement plus A B complement. So we know that A plus A is A only, so this is A complement B complement, and using De Morgan's law it's equal to A plus B complement, so that is NOR. Why I use A plus B complement? Because I want to write in terms of the Boolean gates, NOR or that thing, and options were also given in that like that. That's why I converted into that thing. So I hope you got an idea. Okay, I think we should end the session. That was all for today's session. Thank you. We'll meet next week at the same time, discussing problems related to week 7 from 3 p.m. to 5 p.m. Thank you.